Hey everybody, I want to make this video to tell you about logarithms. So let's just get started. All right, so the first question is always, what are logarithms? So logarithms are the inverses of exponentials. So a logarithmic function is the inverse of an exponential function. That's really what it is. I think I mentioned in the last topic video that exponentials occur all over the place in nature, and they really do. Logarithms, on the other hand, are a creation of man, essentially, and they were made to solve exponential functions or solve exponential equations. And that's really what we're going to use them for, but we want to learn a little bit about them first. So firstly, let's talk a little bit about how to read a logarithm, right? So let's say I have this function. I think we can agree that 2 to the third equals 8. Right, that's I don't think any sort of surprise. So what a logarithm is it's the inverse of this. The logarithm is the exponent, essentially. So I would say that log base 2 of 8 is 3. Right, so if what I have is b to the x equals k, well, let's do a there, then that's the same thing as saying that log base b of a is x. So these guys are equivalent statements to each other. So the logarithm, the value of the logarithm is the value of the exponent that you have to raise the base to get the inside of the parentheses, which is called the argument. So this says that the base to the logarithm is equal to the argument. Now, it's a little complicated, I know. You want to get used to being able to go back and forth from one form to the other because they're both useful. It's both useful to be able to think about things this way and also this way. And the reason is that so here's the idea, basically. The general idea is, if you remember from last video, a really common exponential function, or like in applications, we often get a of t equals a0 times 1 plus r to the t. Right, so this is a really, really common form of function that comes up all the time in common applications. A lot of the time, the thing that you really want to find is t. You want to know how much time it will take for the amount to be a certain thing, right? So let's say your question is, I need to save up $2,000 and I have $1,400 right now and I invested at 3%. How much time will that take to turn into the $2,000 that I need? And that is not an easy thing to find. It turns out that figuring this out is not at all simple, which is why logarithms were invented. Logarithms were basically invented to solve for time in this application. And so that's what we're going to learn about. So we're going to learn basically some properties of logarithms and what they are, so that we can start doing this, because that's the practical thing. So this is what logarithms are. So let's do an example. So let's say I want to know what log base 2 of 32 is equals question. I'm going to call this question mark x, or I'm going to call this thing that I don't know x. Right. So that thing that I'm looking for is I want to know what log base 2 of 32 is. Well, that's equivalent to the question 2 to the x equals 32, or put another way, what power do I have to raise 2 to in order to get 32? And a little bit of investigating will tell you that it's 5, that 2 to the 5th is 32. Equals 32, so x equals 5. Similarly, you can solve for any of these things, right? If I do log base, let's say 3 of x equals 4, well, I'm going to do 3 to the 4 equals x. This says 3 to the 4 equals x. So that means that x equals 81. You can just jam that in a calculator if you don't happen to know that. Similarly, if I want to know log base x of, let's say, 125 equals 3, Well, that's the same thing as saying x to the third equals 125. So if you find out what what number you raise to the third power to get 125 is, it's 5. So you end up with x equals 5 here. Right. So you can solve for all of the various parts of a logarithm by just switching it to exponential form. You want, let me go back here. I'm going to actually, you know what? I'm going to go to the next page. So if we have log base, all right, we're going to do this really slowly. B of x, I'll put that in here, equals a. This is, oh, I think I did this. I did that in the other order when I did this before. Let me keep them consistent. Log base b of a. Whoop. Disaster. I can't write. Let's try this again. Of a equals x. So this is equivalent to b to the x equals a. So just get used to matching these things up when you're solving a logarithm, and also when we're solving exponentials later, when we're using logarithms in future sections to solve exponential functions, we're going to want to start with this exponential and turn it into a log, or we'll do it a little bit different way, but it's the same idea, right? So this b is that b, this a is that a, this x is that x. And you can, like, for right now, I think exponential is probably the easiest way to think of this. So turn your logs into exponentials when you're solving for stuff in logs. That's the basic idea. All right, let me get my outline here to see what else. Oh yes, exponentials. All right, so let's. Oh, well, let me do a slightly worse example of logs, right? So I want to do something a little bit harder than the one we just did, just to sort of show them off a little bit. So let's say I have log base 5 of, I don't know, 1 over 3125. There. And I want to find out what that is. So this is, I'll call that x, right? So this is the thing I'm looking for. So we want to put it in exponential form. I'm going to do 5 to what power? 5 to what power equals 1 over 3125? Well, a thing that you might or might not know is that 5 to the 5th power is 3,125. So I know that 5 to the 5 equals 3125, but that's not the number that I want, right? I want 1 over that. Well, in an exponential, the way you do that is by making the exponent negative, right? Negative exponent means flip everything over. So I can say 5 to the negative 5 equals 1 over 3125. So this number, so x is a negative 5. So x equals negative 5. Similarly, let's do one more. If I want log base 7 of 1 equals something, then my question here is 7 to what power equals 1? Well, the only way to get something to equal 1 with a power is by raising it to the 0 power. And it doesn't actually matter what the base here is, right? 7 to the 0 is 1, 1,000 to the 0 is 1, 18 to the 0 is 1. So anytime you've got a 1 in your argument, you're pretty much guaranteed that the value of the log is going to be 0. So 7 to the 0 equals 1. So I've got x equals 0. There we go. So you can also do this sort of the other way around with fractions. If I do log base 1/2 of, let's say 8, and I don't know what that is. So I want to know 1/2 to what power equals 8. Well, I know that 1/2 to the third power would be 1/8, but of course that's upside down, so I should make it negative, right? So I know that 1/2 to the 3 would be would be 1/8, not negative 8, 1/8. So that tells me that 1/2 to the negative 3 would be 8. So my x equals -3. So here's what you want to remember. If you need to flip something over, make the exponent negative. That'll usually do it. If you are trying to find the log of 1, no matter what the base is here, you probably want 0. The only exception is if you have a base of 0, which you should never have that. But in case it comes up, that's the only case where this doesn't work. And oh yeah, if you need to flip something over, make the power negative. So you can make it you can flip something over by whether this thing is upside down because you want a fraction at the end, or it's upside down because you're starting with a fraction. Doesn't make any difference. Make the power negative to flip it over. That's how you do this. So let's look at what graphing these looks like. Now, I've mentioned that logs and exponentials are inverses of each other, which they are. And so the way we can graph these is by looking at the inverse graphs, right? If you remember, the graph of the inverse of a function is that function flipped over the line y equals x. So here we go. So I've got this log here. Don't worry about the over a part. That's just from the a here. There. So here what I've got is I've got ab to the x and then log base b of x over a. In fact, you know what? I'm gonna make a new one here. Let's do this. Let's do b to the x. So we're gonna add that slider b. We're gonna say this is gonna be called f of x. F of x equals b to the x. There we go. There we go. There's my function. Now I want to do log base b, and if you want to do a base in Desmos, it is you hit the underscore key. Log base b of x. It's going to be g of x. So g of x equals that. All right. So f is my my base function, b to the x, and g is the inverse. It's the log. Right? And I'm also going to do the line y equals x. Y equals x. We're going to make that a little bit nicer looking, make it dotted, give it an opacity of like maybe 0.5 and a width of like 1.5. There we go. That looks nice. And so now we can see that these two things are inverses of each other. So if I want to graph log base b of x, the easiest way is probably to graph b to the x and then find the inverse of it. Right? So I think that's probably the simplest thing you can do. Now you can see here, I'm going to go ahead and call up my my previous graph. It was no, not that one. It was exponential log functions. That guy right there. That's this guy right here, and you can see that I've got it set up where you can see that that the points. So if we've got 2.9160 on the exponential, then we get 6.09 2.91 on the log, right? So that they behave just like just like inverses always do, as you'd expect, right? Right in tandem with each other. And you can see it's going directly across the line y equals x, right? That's perpendicular. So the other thing that I want to mention about this is the idea of an asymptote. So you remember that, what am I trying to say here? So if you remember, when we first started talking about exponentials, we mentioned that when x was getting smaller, so in other words, the exponent was shrinking, you got really, really, really close to the axis, but you never quite got there, right? Like I can zoom in a lot and you can see we're not quite there, right? We never quite reached the axis and we never will. Because here I'm just dividing by 1.7 every time, right? Which will never go to 0 or below it because that would mean that it would be negative, but I'm dividing by a positive number, so it won't become negative like that. So that means that we're going to get really, really close to the axis without actually touching it, and that gives us the concept of an asymptote. An asymptote is a line where that happens, where you get really, really close to the axis without touching it. As you can see, if you go to the left, you have an asymptote at the x-axis. We'll say asymptote y equals 0, right? Y equals 0 is the height of that asymptote, which is the x-axis. because the logarithm here is the inverse of the exponential. Exponential never has any y values that go below 0. That means that when you switch the x and y like you do when you're inverting a function, the logarithm never has any x values that go below 0. And you can see that on the graph, right? Like this never goes to the left of the y-axis. So what that means is because the range of the exponential is only positive numbers, the y's are all positive, the domain of the logarithm is only positive numbers. So you can't put a negative number into a logarithm because those are not in the domain. You can see this in the graph because it never goes to the left of the y-axis. That also means that when you're looking for domains, you actually can't find anything that is in the domain of a log that's a negative number. So we're going to return to that in just a second. Let me make a table of values here to show you how for an exponential and show you how to translate that into a table of values for the logarithm. I'm going to switch my share back to my whiteboard here. Okay, so let's say I have the simplest of functions. Let's say 2 to the x, right? So f of x equals, that's a little sloppy there, 2 to the x. And then the inverse function we know is going to be the logarithm with the base of 2. F inverse of x is log base 2 of x. And so generating a table of values for log base 2 of x is not trivial, right? That would be some work at least. However, generating a table of values for f of x is actually pretty easy. Right, I'm going to do my usual -2 - 1 0 1 2. And as usual, I'm going to start with 0. If I put in 0 into f of x, 2 to the 0 is 1. And because I know how exponentials behave when I increase or decrease the power, I can fill in the rest of this table really easily, right? 2 to the 1 is 2, but I want to think of that as, oh, I increased the exponent by 1, so I multiplied by 2. Same thing here again. When I decrease the exponent by 1, I want to divide by 2. So 1/2, 1/4. There we go. There's my table of values. Now, you might say, well, how does this help me generate a table of values for a logarithm? Well, if you think back to our inverse functions from tables, the table for the inverse function is just the original function flipped over. So that means that I can do this. I can say that x f inverse of x looks this way, right? So all I have to do is take this table that I've got and literally just turn it over. So 1/4, -2, 1/2, -1, 1 0 2 1 4 2. There we go. There, I made a table of values for f inverse of x. Now I have to use the y's that I got out of my table for f as the x's for my new table, but since -2 1/4 is on the graph of f, 1/4 -2 is on the graph of f inverse. So every point on f gives you a corresponding value, or gives you a corresponding point on f inverse, as you can see in my snappy graph here, which I have to tell you, I had so much fun making. This is too much fun with Desmos for me. But like you can see that this point here and this point here are simply just x and y swapped over. So that's how you make the table of values yourself as well. You can do the same thing on your calculator, although I will say TI-83s and 84s don't accept log bases other than E and 10, which we're going to talk about in the next section, or in the next topic, which is those bases. And we'll talk about why those are important. But those are the only ones that your calculator will accept. In fact, do I have that open right now? I do. Let me switch over here for 1 second and show you here. This is from the last topic. So the two bases it will accept are this one that they just call log, and this one, which they call ln. That's an L, not an I. This is log base 10, this is log base E, and we will talk about why you would want those things those things to be the only ones you accept. So you can't do like log base 2 on your calculator without a further trick, which we'll talk about later, called change base property, which don't worry about it right now. Basically, right now, I just want you to know how the graph of logarithms look and how to generate an XY table so that you can graph it by hand and on a calculator as well. Now, I like Desmos for this, obviously. The Desmos app, by the way, I cannot recommend it enough. It's fantastic. It will do all of this. It has all the functionality of Desmos. Get it for your phone. It's free. Costs nothing. I use it all the time on my phone. It's really great. Yeah, so that's how you graph a log function. Is basically you graph the exponential function, then reflect it over the line y equals x. And if you're having trouble doing the reflection, well, you can just make a table of values for the exponential function and then flip it over for the inverse, and then that'll be the log, right? So that's the easiest way to do that I know of anyway. So you can whatever exponential function you got, you can see all I've got here is just a log and an exponential, and they're clearly inverses of each other. So yeah, is that the last thing I want to talk about? No, I want to talk about finding the domain of a log function. So let's do that. All right, so let's say I want to find the domain of a log function. So let's say I've got the function f of x equals log base 3 of 2x plus 5. Let's say I want to find the domain of that function. So the domain of that function, now, as we mentioned, you can't take a log of a negative number, right? So any negative number in here is a problem. And in fact, 0 is a problem too. You can't take a log of 0 either. So what I need this stuff inside to be positive. So I can actually write that in inequality. I can say that 2x plus 5 has to be greater than 0. Otherwise, I'm going to have a problem because you can't put in 0 or negative numbers into your log. And so I just solve that. That's literally it. I'm going to subtract 5 divided by 2. So we got 2x is greater than negative 5. Note, I don't have to flip the inequality over there. I subtracted 5, not multiplied by it. Not multiplied by negative 5. And then I divide by 2. And so x is greater than negative 5 over 2. And that is my domain, right? And if I want to write that in interval notation, I would write it as so let's look at it as a number line so we can see what this looks like. Negative 5 halves. So I want all of the stuff that is bigger than this. So not including, so open circle there. So that means my left endpoint for my interval notation is negative 5 halves. So we get this, negative 5 over 2, and we're going to go up to positive infinity. So go to the right forever. So that's my domain. You can write your domain in any of those ways. This is fine. This is fine. This is fine. On tests, I will often ask for all three just to make sure that you can convert between them, because it is important to be able to understand when somebody writes like this and also have a visual representation of what that is and know what it means in inequality form. So this is the domain of this log. Now, you can certainly make this a little bit fancier if you want to, but the basic idea is that whatever goes in here, whatever goes in the argument, that's called the argument, in the parentheses, has to be positive, has to be greater than 0. And so you literally just take that, set whatever's there, greater than 0, solve the inequality. That's how you find the domain. All right. I mean, I was going to do some applications of logs, but I'm not, because there kind of aren't any. In a sense, it's not really true. There are very, very few applications of log functions, except as they relate to exponential functions, in which case there are tons. So when we learn a little bit more about logarithms, we'll learn a couple properties, change base property and the, what do we call that? Product property of logarithms. And we will use those in exponential applications, which is where they're really useful. Logarithms on their own, not a thing that you will like. You could go your entire life without ever encountering a logarithm in the wild. They're not just running around the forest or whatever. However, when you need to solve an exponential equation, that's when you want them, and so that's how we'll use them. I'm not gonna do a bunch of other stuff with them. Yeah, so that's what we're gonna do with them. So I'm not actually gonna solve any applications right now. However, we're gonna have some applications a little bit later when we get to exponential function applications. Then we will be using logs all the time. So you're gonna want to know the basic properties of them. All right, that said, I think that's all I wanted to say about logarithms, excuse me. So I'm going to go ahead and stop that here. Actually, let me just check my outline. I'm going to be sorry if I have more to do. Nope, we're good. Okay, I'm going to go ahead and stop the video here, and then I will, oh my gosh, I'm stumbling all over the place. I'll see you guys in the next video.